Thank you. All right. Third-party code is great. It's fantastic. We've got libraries for doing regexes, for HTTP, for making me angry when I'm making slides. But third-party code operates in an environment where our applications deal with users' data. And this situation is everywhere. It's not just in whatever application you're writing right now. It's in your web browser with extensions. It's in your phone. It's everywhere. Third-party code is freaking scary. So we've got JavaScript libraries stealing your environment variables, Python libraries calling back to the great land in the east, Chrome extensions being malicious, and this stuff is all over the web. Everywhere we've got problems with third-party code that we can't trust. So this has motivated a research question, and the question is, how do we integrate untrusted third-party code in applications or environments where we're dealing with users' sensitive data? All right. So this is the solution. Information flow control. This is why we're all here. This is the topic of the session. So what kind of techniques have we got? Well, we've got language-based techniques for this mostly. So we've got static techniques like type systems and theorem-proving based techniques for ensuring that the third-party code that you're integrating into your system is well-behaved with respect to privacy and security. We've got dynamic techniques like inlining monitors and special runtime systems. And this talk is going to be about the second kind. All right. So what do these kind of systems do? Well, here we've got a piece of code. We read Max's secret. We set Tom's variable to 0, and then depending on if Max's secret is greater than 0 or not, we update Tom's variable. We write Tom's variable to a file. Okay? This is obviously insecure. Most systems will reject this because by observing Tom's file, Tom can tell something about Max's secret. However, if I change this program to look like this, now Tom, by inspecting his file, will not be able to tell anything about Max's secret, because regardless of Max's secret, 0 will always be written to Tom's file. However, most systems will reject this program too. Not all, but most. And this is a false alarm. This is not what we want. We want to make information flow control practical. Okay. So what are we going to do? We're going to build on an idea, which has been around for sort of 10 years or so, of multi-execution. So what's the idea? The idea is you take your third-party code that you don't trust, and you run it multiple times in slightly modified environments to ensure that it preserves the security guarantees that you want to preserve. All right. So to this mix of systems for doing this, we add our main contribution of this paper, Multef. Multef is both a theoretical framework and an implementation in which you can write your third-party code, which ensures the security guarantees that you want to have and the guarantees you want with respect to users' data is preserved by multi-execution. Okay, so to understand how Multef works, we're going to have to understand two main concepts. The first concept, due to Austin and Flanagan, is the idea of a faceted value. So looking back at the program we had before, we had two variables, Max and Tom, and these variables have associated with them different views. So what the funny notation that we have here with the brackets and the question mark means is that if you get to see Max's stuff, then you see 42. Otherwise, you see 0. 0 is just some default value that we pick for people who are not allowed to see Max's sensitive data. And for the variable Tom, well, we assume that the program text that you're running is public, so the variable Tom is always going to have the value 0 here. Now, by the way, I should say this funny notation with the double colon, that is just to say that the variables Max and Tom have type a faceted integer. That is an integer with all these different views. So the situation we have is like this, right? Every variable is going to be some form of tree like this. Going down the left, you will have what you see if you get to see Max's stuff. Going down the right, what you see if you don't get to see Max's stuff. Okay, so we can also compute with faceted values. And this is a key contribution of Austin and Flanagan. We have a principal way of computing with them. Right? So if you have this value, Max 42.0, Tom 10.1, and we combine them, we get this slightly bigger value right here. And how does it work? Well, following left-hand sides for now, right? Assume you get to see Max's stuff, Tom's stuff. We follow the left-hand arrows, in the result, we get 42 plus 10, 52. Same story if we don't get to see Tom's stuff. 42 plus 1 is 43. Okay. All right, I should say too that, of course, this follows analogously for the rest of the computation. All right. So the second important concept, FIO computations. These are computations in which we allow side effects. Okay. So what have we got here? We've got a very simple program. We read a file, Tom's file. We write back to Tom's file just the value that was in the file plus 1, assuming there's an integer in the file. Okay. So this is a straight line program. There's no branching control flow, nothing interesting going on. But still, we're going to have that n here is a faceted integer. Okay? So what's going to go on? Well, what if we want to somehow branch on n? What if we want to do something interesting? Well, we can't do this here yet. So let's look at how to do that. So here we have an even simpler program than what we had so far. Depending on the secret B, we either write hi to Bob's file or we write bye to Bob's file. What's B? B is a value like this. If you get to see Bob's stuff, then it will be some secret sensitive to Bob, maybe true. Otherwise, it will be some default value, conveniently false. Okay, so what we end up with now is a computation that looks like this. The computation itself has two different views. If you get to see Bob's stuff, the computation is write hi to Bob's file. If you don't get to see Bob's stuff, the computation is write bye to Bob's file. And this computation of itself is a faceted value with computations that it leaves. Okay. Now this is slightly uncomfortable. I mean, I talked about faceted values and values, and now I'm putting computations and values and mixing them, and this is very, very tricky stuff. So I'm going to simplify it by introducing the third most important concept. And why is it the third? Well, it's 1 plus 2. Here's how we combine faceted computations and turn them into computations that give you faceted results. So what we have is you take as input one of these faceted computations coming from some control flow structure of a faceted value, and you get back a computation which gives you back a value, a faceted value. This is the only primitive in our system which has the capacity to introduce multi-execution, and it's the core primitive which allows our system to subsume previous approaches. There's some asterisks on that, but you can ask me later. Okay, so what have we got? In this case right here, where we're executing this program that we saw before, what we're going to do is we're going to run hi, write hi to Bob's file, we're going to run bye, and we're going to write bye to Bob's file. But this doesn't make much sense. Why would I write bye to Bob's file if I've already written hi to Bob's file, and I know that if I get to see Bob's stuff, then the secret is true. So this doesn't make any sense. We shouldn't be writing bye to Bob's file here. And in fact, the system as it stands, and as the previous work on which this builds also does, is just silently ignore this output here. Okay? So is this always the case? Do we always ignore the output when we don't get to see the secret? Of course not. Otherwise, this would all be very trivial, and we wouldn't be here. So here's a program which would be rejected by common systems, right? Now, you see that we have some control flow branching on Bob's sensitive value, and in both the computations, we write to a public file, right? So this would be rejected typically because we're writing to a public file in a sensitive context. However, what we see is that the write will be the same in both the branches of the if, so it doesn't matter. And under multef, what we'll do is that when we're in the sensitive context, running the you get to see Bob's stuff, we'll only perform the hi write. And if in the other context where you don't get to see Bob's stuff, we'll only perform the public write. Okay. Now, one more example. What about this program? Depending on B, you either loop forever or you do nothing. And then we write to a public file. Done. Okay, let's see how this executes. It's a program like this. Loop or skip, and then write done. So we're going to loop forever. And then we're going to skip and we're going to write done. Except that's never going to happen because we're looping forever. Now, observe that depending on the real value of B, the value that you get to see if you're Bob, the write to done will either happen or not happen. This means that an attacker observing the public output on the public file will be able to tell something about the secret B depending on whether or not this program terminates. Okay, fine, termination, you say, it's not a big problem. It's just one program not terminating or terminating. But if the attacker is able to launch many copies of this program, e.g. by web requests or whatever, right, then the attacker is suddenly able to parallelize this attack, which leaks 1 bit, and now you can leak an entire secret very quickly. All right. So here's one of our key contributions, Faceted Secure Multi Execution, a way to mitigate these timing attacks, or termination attacks, I should say, while still remaining within the same way of executing. So what we're going to do is, before starting loop, we're going to say, okay, you can loop, but you're going to have a timeout here. And this is always going to be the case. When we're running a computation, we're going to give it a timeout. Okay? Now, since this is looping forever, it's going to hit the timeout. We're going to spawn a new thread in which we're going to run the other computation, the skip, and then write done. And just in case we were wrong about this thing not terminating ever, we're going to have to copy up whatever is left after the control block has finished into the first computation. Now here, that would be silently ignored, but you can imagine a more complex computation than done. All right. So what we have is, in this FSME mechanism, this timeout mechanism, we have some form of knob that we can use to sort of vary one aspect of the way the system behaves. Okay. What does this mean in the extreme cases? Well, in the extreme cases, the first one we've already seen, that's when we set the timer to infinity. We have these termination attacks, and this corresponds exactly to something that's in the literature called multiple facet semantics. Okay. This is one of the previous approaches that I mentioned. Now, curiously, if we set the timeout to 0, we also subsume a previous approach called secure multi-execution. What this system does, or what FSME does under these circumstances, I should say, is just launch everything in parallel and copy up the rest of the program up into every thread. Okay, makes sense? Good. Now, we've talked about weird ways of running programs, termination. We've talked about views of different data with if you're max, if you're not max, if you're Tom, all sorts of stuff. So what can I say about security? Well, I can say precisely what I want to say about security. I can say we have termination-sensitive non-interference. That means you can't leak data by termination attacks, and information does not flow from Bob's file to Tom's file unless this has somehow been approved beforehand. And the other theorem, which is for reducing or for removing false alarms, is transparency. This is to say that a program which is secure by construction or secure a priori does not have its semantics altered up to some asterisks we can talk about offline by running in our system. And I should say, finally, all our contributions have been mechanized in the cockproof assistant. All right. Now, what are the performance implications? Because, I mean, it's fine to have security, but if you have no way of being practical by sort of exploring how should I run my program with this knob and everything, somehow we need to be able to talk about the performance. So we've done some benchmarks. We've done benchmarks mainly to look at the key primitive, right? This control thing which introduces multi-executions. So here's the first one. You just have a full faceted tree like this with big, heavy computations at the nodes. For details on how you might construct this, refer to our paper. So here's the first curious little thing. On the y-axis, you see the memory consumption, and on the x-axis, you see, as we vary the size of the tree, the number of computations that you have to perform. In red, we have SME, which is just running with a 0 timeout. In blue, we have MF, that is running with an infinite timeout. And in green, we have something in the middle. I think the timeout is 1 second in this example. It's not, the precise details are not important. We'll see more what happens when you vary it later. But here we see a story, right? So memory consumption is through the roof for SME, but SME, as we see in this wall clock time measurement, is way faster. And curiously, with the timeout set to precisely the magic value of 1 second, somehow we can achieve a result in the middle of these two as well. Okay, so is the story this simple, right? You have, if you set a short timeout, then that's great if you've got many cores and lots of memory. If you set a long timeout, that's great if you don't have much memory, but you have all the time in the world. Of course, it's never that simple. So here's the second benchmark. We just run some lightweight computation at the leaves of the faceted tree, and afterwards we run some big, heavy, time-consuming computation. Now, SME behaves the same in terms of memory, so that's all well and good. However, for time, now suddenly SME is performing way, way worse. And why is this? Well, remember, if we go back, remember this. I'm copying up the rest of the computation into every thread. So the big, heavy dumbbell that we saw is going to be copied up into every parallel thread that we spawn. Not great for performance. So performance is application dependent. And this is one of the key findings here, that as we put all of these things into one framework, it turns out that you're going to have to start doing some experiments, start running, start testing, start figuring out where the performance of your particular third-party code lies with respect to the rest of, with respect to this timeout parameter. I also told you that I would show you what happens when you vary the timeout. Sorry, yeah. To show you what happens when we vary the timeout. So here's the first benchmark, run again with the timeout varying from 0 to infinity, right? Or infinity, a very big value. So in red here, we have something which is very similar to secure multi-execution, which is running with a very short timeout. And then as we increase the timeout, our approach starts looking more and more like multiple facet semantics. All right. So in this talk, we've introduced MultEF. It's a system for unifying previous approaches to multi-execution. We have security guarantees, termination-sensitive non-interference, and transparency mechanized in the Coq proof assistant. We have an implementation of the framework in which you can write a third-party code in Haskell. In fact, all of the code I showed you is code that will run just fine in the framework. We have this novel way of running multi-execution programs with a timeout, which satisfies the termination-sensitive non-interference. And we have some of the first benchmarks comparing secure multi-execution and multiple facet semantics. And also showing how we can vary in between the two. All right, I think that's it for me. Thank you very much.
Any questions?
Hi, Isaac Sheff, Cornell. Do you have any manner of declassification?
No. Not yet.
Beginning of the talk, you motivated your approach by saying the third-party applications are dangerous. So have you tried any third-party applications in your framework?
Oh yeah, I didn't include that here, but we have a case study where we implement a service which is sort of like a plugin service for your Dropbox, where third-party components are written in the framework, the MultEF framework, then executed many times with respect to the contents of your Dropbox. Well, I mean, I think that answers your question basically, right? Yeah.
Any other questions?
Andrew is either leaving or coming up to ask a question. Oh, crap.
So I was just thinking about your performance numbers.
Mm-hmm.
You're running all of this stuff, I think, in the same framework.
Yeah, same environment. Yeah.
So one of the benefits of the original SME stuff was that you got to run the applications more or less unencumbered by extra machinery. But here, everybody's being encumbered by the same machinery. So I guess I'm wondering, how much overhead is getting added by the fact that you have this machinery, and presumably the SME numbers would actually get scaled down if you're running in the pure SME system. Although I think it is really nice to be able to switch between the two different modes that and so that is cool. But I'm still wondering, how much are we paying for having FSME around as an option?
That's a good question. I mean, so this I would expect to depend entirely on your application, and on your implementation of the framework. So one problem you have with traditional SME, where you're running in a black box fashion, is that you actually end up with way more parallelism than you would like. So our system supports a decentralized label model, which you cannot get in secure multi-execution, right? So we only create these threads precisely when you need to create a new thread. So in that sense, you want to talk about the sort of more theoretical bounds, I can say that our system will never create more parallelism or more parallel running threads than a standalone black box SME distribution or a SME solution. Does that answer your question?
So that's helpful, but there's also some overhead happening here, I think, because of the data representation.
That's right.
Right. So you have facets all the time, and I think when you're in the pure SME mode, they're very, very small, simple trees, but there's a tree there nonetheless.
Yeah.
So should I think of it as you get to run the original program, but all the values kind of have one level of container wrapped around them? It's like one extra indirection, or
yeah,
is that
that's
fair?
kind of how you would have to think about it.
Okay,
yes.
That doesn't sound terrible.
It's not. I mean, sorry. Actually, log n extra containers.
That's if you have, but that's if you have like n.
Yeah, if you have a deep tree. Yeah.
I guess I'm just imagining, the sort of original SME papers, that it was really just high versus low.
Yeah.
And then you got two runs.
Yeah.
And then the question is, how much are you paying?
So in high versus low, you would pay the price of one extra memory cell.
Yeah.
For our representation. Yeah, that's exactly right.
Okay, thanks.
Okay, let's speak again. So let's continue the session.